Hi, in this session we'll be discussing about isomorphic graphs. Okay, so what do we mean by isomorphism? So isomorphism is basically the mathematical way of saying that two objects are equal. Okay, we have already studied about isomorphism when we had studied about algebraic structures or groups, etc. in our earlier semester. So isomorphism is nothing but the mathematical way of saying that two objects are equal, exactly the same. Okay, so how do you say shows how that two graphs are equal? For example, if I draw two graphs, for example, if I draw two graphs like this, and if I label them like A, B, C, D, and 1, 2, 3, 4, you can essentially see that these two graphs are exactly the same. Only the difference is that there's a difference in their labeling. Okay, but essentially they have the same properties and everything. So I'll say that this group has the same number of vertices as the second group, and similarly the edges are the same, and also the corresponding edges has the same n vertices as the so corresponding edges in the second graph has the same n vertices as the corresponding edges in the first graph. So all these properties, if two graphs satisfy, we'll say that the two graphs are isomorphic. Okay, so isomorphism basically means nothing but the two graphs are essentially the same except for labeling. That means they will have all the common properties, like they will have the same number of vertices, same number of edges, and the edges will be having the same corresponding vertices as the what do you say, the endpoints, and also all other properties. Also we'll be studying more properties of graphs in the later classes. And so all those properties will also be satisfied by these isomorphic graphs, because we will be studying, for example, what is the complement of a graph, what do we mean by an adjacency matrix of a graph, etc. So all these things will also be the same for both these graphs. Okay, so essentially isomorphism means that two graphs are exactly the same except maybe for the labeling. Okay, now how do you define it mathematically? It's very simple. I'll say that two graphs are isomorphic if first of all there is a function from the first graph to the second graph. Okay, the function from the vertex set of the first graph to the vertex set of the second graph. Okay, so which is 1 1 and on 2. Why I'm saying this? Because 1 1 and on 2 means it just means that the graphs have the same number of vertices. Okay, so if it is a 1 1 and on 2 function, that means we will know that the two set has the same cardinality or the same number of elements as there. So I'll take a 1 1 on 2 function, so that the first vertex and the second vertex have the same number of vertices. Plus I'll impose one more condition there. I want to show that the corresponding edges in the first graph is the same as the corresponding edges in the second graph. So I'll impose a condition that one more condition, that means if a comma b is an edge in the first graph, then correspondingly f of a, f of b will be an edge in the second graph. That's it, sir. Okay, so what are the two conditions? So suppose I have two graphs g comma h. Okay, so these two graphs are isomorphic if there exists a function f from vertex set of g to the vertex set of h, which is 1 1 and on 2. Okay, so with this condition we will be getting that the vertex both the two graphs has the same number of vertex. Okay, now the next condition I'm going to impose is that if suppose v1 comma v2 is an edge in g, so that means if v1 v2 is an edge in g, I'll have to have f of v1 comma f of v2 should be an edge in h. Okay, so it should be an edge in h. Okay, so the corresponding edges, so the n vertices of the edge is the same as the n vertices of the corresponding edge in the second graph also. So though if you impose these two conditions, we'll get that essentially the two graphs are isomorphic. So if you look at this graph which I've already drawn here, you can see that here a is being mapped to 1, right? A is being mapped to 1, B is being mapped to 2. So there are many type of isomorphism you can define here. So D is being mapped to 4 and C is being mapped to 4. 3. So if I say that I'll just explicitly say that f of, so f is defined as f of a is equal to 1, f of b is equal to 2, f of d is equal to 4, f of c is equal to 3. Okay, so what can I say? So if here ab is an edge in the first graph, so similarly you can see that f of a, f of b, that is 1 2 is an edge in the second graph. Okay, so that condition is satisfied. Similarly ad is an edge in the first graph, and similarly f of a, f of t, which is 1 4 is also an edge in the second graph. Okay, so you can see that the corresponding vertices and corresponding edges are just the same. Okay, so in the first set of problems, when you are being asked to show that two graphs are isomorphic, you have to explicitly show or give me an isomorphism. You have to say what is f of a, what is f of b, what is f of 6, and everything. So you have to explicitly give the isomorphism. Okay, so in the later view of the course, we'll study some important methods from which we can show that two graphs are isomorphic. So after we have learned some more concepts, I'll show you an easy way to show that whether two graphs are isomorphic or not. So in the first set of problems, we will be explicitly saying the mapping which makes the two graphs isomorphic. Okay, so if you want, you can read it. So it's a bijection. So basically, isomorphism is a function between the vertices of G and H such that any two vertices in U and V or G are adjacent to if and only if f of u and f of v are adjacent in H. Okay, so that is the definition of isomorphism. Essentially, it means that both the graphs are same. So here you can see I have drawn some isomorphic graphs here. So all the four graphs are actually isomorphic. So let us try to bring an isomorphism here. Okay, so suppose we are going to label this. Suppose I am going to label this as A, B, C, D. I am going to label this as P, Q, R, S. Okay, so before we do this problem, we have to remember one thing. When two graphs are isomorphic, they will have the same number of vertices, same number of edges. Okay, and the corresponding edges would be the same. So that means they will have the same degree sequence. Okay, so it will have the same degree sequence. Okay, and the degree of the corresponding vertices will just be the same. That is why it will have the same degree sequence. And now there are also other properties. I have already told you they will have the same, what you say, adjacency matrix and everything, same complements and everything. So essentially these are the same. So even if any of this is violated, these two graphs will not be isomorphic. For example, if the number of edges is not the same, then the graphs will not be isomorphic. If the degree sequence is different, the graphs will not be isomorphic. Okay, so and also there are other methods also. We will discuss them in the problems now. Okay, now if I now look at the come to this problem. So we have two graphs and we have labeled it like this. Okay, let us try to show that the two graphs are isomorphic. Okay, so for that I have to explicitly give an isomorphism. So I have to give a where f of a is. I have to say where f of a is being mapped, where b is being mapped. So I have to say to which vertex f of b will be going, to which vertex f of c would be going, to which vertex f of d would be going. Okay, so where should a go? Okay, so if you look at this figure closely, you can see that a has a degree 3, so it should be mapped only to a degree 3 vertex. So it is very important. So here a has two possibilities. It can either go to q or s. Okay, so there can be many isomorphism. It can either go to q or s. So let us go to q. Okay, so for simplicity I am just choosing it as q. Okay, so a is going to q, so that means now where will b go? Now b will has two possibilities. B should be near to a. So so when a has gone to q, b should go to either p or r. Okay, so b should go to either one second. So if a has gone to q, this should go either to either what is it? Sorry, I have made a mistake here. Just a second, because here actually p is not a vertex there. The vertex is actually only this one. Okay, so the vertex is actually inside, so p is inside here. Okay, so please pardon me. Okay, now look at this. So a has gone to q. Now b is adjacent to a, so b should be b should either go to p or r, with both of them which has degree 2. Okay, so you can take anything you place. Suppose I am taking b as r, I can also take it as p, no issue. Okay, so if f of p I have chosen it as r. Okay, is it clear? Okay, now where will c go? C is actually adjacent to b and it has degree 3. So you have to look at a vertex which is adjacent to r and having degree 3 other than q. So it is actually your s here. Okay, so c has gone to s. Okay, and what is d? D is again only one is left. So what is it? It is actually p. So this is the one onto mapping I have done. Now let us check whether it has the same property as that of have preserving the adjacency of vertices. Okay, so if you look at AD is a vertex in the first graph, so you have to see what is f of a, f of d, is it adjacent in the second graph. So f of a, f of d would be f of a is q, f of d is p. So yes, qp is there a edge in the second graph, so they are adjacent there. Okay, similarly AC is a edge in the first graph, So what is f of a, f of c? Are they adjacent in the second graph? F of a, f of c would be q comma s. Okay, so q comma s is also adjacent, so that they are also preserved. Or similarly, if you look at DC, you can see the corresponding edges would be f of d, f of c, which is sp, that is also an edge in the second curve. So now if you look closely, you can see that all the vertices and the corresponding edges are being preserved, therefore the two graphs are isomorphic. So you have to write this out explicitly to show that two graphs are isomorphic. You have to give the mapping and you have to say which all vertices are going to which all vertices, and then you have to give the all corresponding, you have to write about the corresponding edges, then you can prove that it is isomorphic. Okay, so in the later chapter when we study adjacency matrix, it will be very simple method to draw it. So for now, for our purpose, for now we will now basically write out everything. We'll write out all the vertices and all the corresponding edges, and we'll say that this vertex is being mapped to this vertex, and correspondingly we can see that this edge is being mapped to this edge. Okay, so this is how we'll be proving the graphs are isomorphic. Okay, now you can try at these two problems also to try to show that they are isomorphic or they are isomorphic. So please try it out. So you have please try to label it out. Okay, now let us look at some examples also. Okay, so you have to look at some important points here. Okay, so isomorphic graph must have the same number of edges and same degree sequence. Okay, so I already told you it has the same number of edges, vertices, and same degree sequence. Okay, but that doesn't guarantee that the graphs are isomorphic. If the graphs are isomorphic, it will have anyway, it will have the same number of edges, anyway it will have the same number of vertices, it will have the same number of degree sequence, but essentially it should preserve the corresponding edges also. So that is an important condition there. So if two graphs has the same number of vertices and same number of edges alone does not mean that the graphs are isomorphic. Okay, so we will see some examples here. So look at these two graphs. Okay, so if you look at these two graphs, how many vertices are there? 1 2 3 4 5 6 vertices are there. Here if you look at these two graph, 1 2 3 4 5 6, here also 6 vertices are there. How many edges are there? 1 2 3 4 5, 1 2 3 4 5, so 5 edges are there. And what is the degree sequence? It is 1 2 2. Okay, so if you write down the degrees, so this will have degree 1, this has degree 2, this has degree 2, this has degree 3, it has degree 1 1. So the degree sequence would be 1 1 1 2 2 3. In this graph, what is the degree sequence? Here there is 1 is there, 2 is there, 3 is there, 2 is there, 1 is there, 1 is there. So 1 1 2 2 3, 1 1 1 2 2. So it has the same number of degree sequence. Okay, now are these graph isomorphic? Okay, so if you look at this graph, if you look at this x point, okay, so what is the degree of, so if you look at this x point, what is the degree of this x vertex? Its degree is actually 3. Okay, now you can see that it is adjacent to vertices of degree 1 1 and 2. Okay, now look at this graph again, and now this x vertex should be mapped, can only be mapped to the y vertex in the second graph, because there is only one vertex of degree 3 there. Okay, so this can only be mapped to y vertex of the second graph, but the y vertex, if you see closely, you can see that its adjacent vertices have degree 2 2 1. Okay, so but here the adjacent vertex have degree 1 1 and 2. So what's the problem with that? That means you can't draw, you can't find an isomorphism which preserves adjacency there, because in the second graph this x will be going to two vertices which will have in effect of degree 2. Okay, but in the what happens in the first graph? In the first graph, x is going to two vertices of which has degree 1, but in the second graph we can't find two vertices like that, we can only find one vertex with degree 1. Okay, so that means you can't map x to v. Okay, so because if it was an isomorphism, when x is being mapped to v, we should also have two adjacent vertices with degree 1, but here it is not possible in this graph. Okay, so if you look at closely, you can see how fine these points are. Okay, when looking at, first of all, we'll think that these two graphs are isomorphic, but because of this adjacency problem, they are not isomorphic. Okay, so it should have the same vertices, have the same edges, should have the same degree sequence, but that alone is not sufficient. The adjacency must also be preserved. Okay, so these two graphs are not isomorphic, so you have to be careful when you decide whether two graphs are isomorphic. Okay, so similarly, let's do some problems now. Okay, let us check whether these following graphs are isomorphic. Okay, now look at this first problem. Okay, so can you look closely? the first thing you have to check is that you have to look at the number of edges, number of vertices, then you have to look at the number of edges, then you have to look at the degree sequence, then you have to look at the possible way of mapping it. Okay, look now, look how many vertices are in the first map, first graph. It is 1 2 3 4 5, 5 vertices are there. Okay, so second graph 1 2 3 4 5, 5, so it is satisfied, 5 vertices are there. How many edges are there? So here it is 1 2 3 4 5 6 edges are there. Here 1 2 3 4 5, only 5 edges are there. That means it does not have the same number of edges, so that it is not isomorphic. Okay, now in some textbooks, when two graphs are isomorphic, they'll just write the symbol G is isomorphic to H. Okay, so it is there in some textbooks also. If it is not isomorphic, they'll bring a cross sign. Okay, now look at the second graph. So I hope it is clear. The first graph, they are not isomorphic. Now look at the second graph. Okay, so in the second graph, how many vertices are there? Both has 4 vertices. How many edges are there? 1 2 3 edges are there, right? So 1 2 3, so both has 3 edges. Okay, now let us look at the degree sequence. What's the degree sequence here? Here it is 1, here it is 2 2 1, so 1 1 2 2. Okay, here 1 2 2 1, so again you have 1 1 2, so degree sequence is also satisfied. So this may be isomorphic. I don't know it is isomorphic, it can be isomorphic. Okay, so now let us try to write down an explicit isomorphism. Okay, so how will you do that? So okay, it's very simple. So you take any vertex, try to map it to another vertex in the second graph. Okay, so if I take the first vertex 1, okay, it should be mapped to, so it is of degree 1 here, so it should be mapped to a vertex of degree 1 in the second graph. So it can be either mapped to A or C, so it can either go to A or C. Suppose I am taking it as A. Okay, now 2 is adjacent to 1, so therefore 2 should be mapped to adjacent vertex of A, which is actually B. Here also no issue, B has degree 2, 2 also has degree 2. Okay, no issue. Okay, now 3 is adjacent to 2, so 3 should be again mapped to D. Okay, now 3 has degree 2, D has also degree 2, so far no issue. Okay, similarly 4 is adjacent to 3, so it should be mapped to C. Now 4 has degree 1, C has degree 1, so all has the same adjacency. Now we can see that if 1 2 is an edge there, AB is the corresponding edge in the second graph. Okay, it is satisfied. If 2 3 is an edge there, correspondingly BD is also an edge there, so that is also satisfied. Again 3 4 is an edge here, so correspondingly CD is also an edge here, so that is also satisfied. So I hope that is clear. Okay, so these two graphs are essentially isomorphic. Now look at this problem here. Let us see whether these two graphs are isomorphic. Okay, so first of all, for our first results, look at the number of vertices. How many vertices are there? 1 2 3 4 5, 1 2 3 4 5, so 5 vertices are there. Okay, how many edges? 1 2 3 4 5 here 1 2 3 4 5, so 5 edges are there, so that is satisfied. Now what is the degree sequence? 2 2 2 2 2, here also 2 2 2 2 2, so that is also satisfied. Okay, now let us try to bring an isomorphism. Okay, now let A, so A can be, A is of degree 2, so it can be mapped to any vertex of degree 2 here. So it can, with the same two graphs are isomorphic, and maybe you can bring about many isomorphisms. So here A could be mapped to A dash, B dash, C dash, D dash, or E dash. So let us assume that A is mapped to A dash. Okay, so I am trying to show that A is being mapped to A dash. Okay, now where will B be going? Now B is adjacent to A, so B should either go, it cannot go to B dash, because B dash is not adjacent to A dash here. So be careful. So here B is adjacent to A, so here B has two possibilities. Now it can either be C dash or D dash only, because it should be adjacent to A dash to preserve adjacency. So B can be, I can say, let B goes to C dash. Is that clear? Okay, and similarly now C is adjacent to B, so here correspondingly your C, the image of C should be adjacent to C dash, so it has two possibilities, either A dash, so okay, so A dash has now been mapped to A has been mapped to A dash, B has been mapped to C dash. Okay, therefore C has to be mapped to definitely E dash. Okay, so only that is only adjacent vertex which has not been mapped there. Okay, and D should be adjacent to C, so it will be B dash. Okay, and therefore E finally adjacent to this, so therefore it will be mapped to D dash. Okay, and you can see that correspondingly E is also adjacent to A. Okay, so this is how I have mapped it. If I have chosen A as something else, your mapping will be different here. Now you can check the edges here. Here AB is an edge in the first graph. You can see that A dash C dash is an edge in the second graph. Okay, similarly CD is an edge in the first graph. Correspondingly, E dash B dash is an edge in the second graph. Okay, similarly, if you can see that D is an edge in the first graph, correspondingly B dash D dash is an edge in the second graph. Now you can verify all that. Now we will get that these two graphs are essentially isomorphic. Okay, so it's very simple. You have to be always look at where this closely. Okay, now look at, let's say, this last problem. So I hope it is clear now. Okay, so please write down the corresponding edges also. Okay, now let us look at this last problem. Okay, so I have given you two graphs. You have to show that whether these two graphs are isomorphic. Okay, now how many edges are there? First, how many vertices are there? First of all, there are 8 vertices are given, right? Okay, in the first graph there are 8 vertices. In the second graph, that also you have 8 vertices. So 8 vertices. How many edges? 1, 2, 3, 4. Again 8 plus 2, 10 edges in the first graph. How many edges in the second graph? 4, 8, 10 edges in the second graph. And what's the degree sequence? So this has degree 2, this has degree 1, 2, 3, 3, this has degree 2, this has degree 3, this has degree 1, 2, 3 here, this has degree 3 here, 1, 2, 3, this has degree 2, this has degree 2. So that is a degree sequence. So degree sequence is actually 2, 2, 2, 2. Okay, then 4 2s and then 3 3, 4 3s, 3 3. Okay, second graph, if you look at this, 3, 2, again 2, again 3, this is again 1, 2, 3, 2, 2, 3. Okay, so the degree sequence is also the same. Okay, so they can be isomorphic. I don't know whether it is isomorphic, they can be isomorphic. Now let us try to bring an isomorphism. Okay, so where will V1 go? Okay, I have to give a map to V1. So V1 is of degree 2, so it can go to either, it can go to V2 dash, V3 dash, V7 dash or V5 dash. So 4 possibilities are there for V1 because V1 is degree 2, it should be mapped to a vertex of degree 2. So it can either go to V2 dash or V3 dash or V7 dash or V5 dash. Okay, now so which one will you choose? Okay, so if I choose V2 dash, can I choose V2 dash? Okay, if I choose V2 dash, the problem with V1 is that V1 has 2 vertices, adjacent vertices of degree 3. So V1 should have 2 adjacent vertices of degree 3 here. Okay, so here there is a degree 3 is there, here degree 3. So we have to choose a vertex accordingly which has 2 adjacent vertices of degree 3. Okay, so if I choose V2, this vertex this vertex has degree 3, but this vertex has only degree 2, so V2 cannot be chosen. Okay, because V1 has 2 adjacent vertices of degree 3, but V2 has only one adjacent vertex of degree 3. Okay, so can I choose V3 again, V3 dash again? That also has the same problem because it has only one adjacent vertex of degree 3, so V3 cannot be chosen. Now look at V7 dash, can it be chosen? With the same argument, V7 dash can also be not chosen. Okay, similarly V5 dash, okay, that also cannot be not chosen because there are no vertex of degree 2 in the second graph which has 2 adjacent vertices of degree 3. V1 has that property, but no, there is no other vertex in the second graph with that property. That means we can't map V1 to another vertex in the second graph preserving adjacency. That means essentially these two graphs are not isomorphic. Okay, so it's as a basic idea. So that is it. So I hope it is clear. So we have to try more problems. You have to give an explicit you have to try to give an explicit function. You have to look closely whether the degree sequence is being preserved, whether the corresponding vertices are being preserved. Only then you can say that the two graphs are isomorphic. Okay, thank you.